Hello students, this is Dr. Anita Raj, your chemistry mentor, welcoming you for one more important session in transition elements. Today we shall see D block elements in one shot. That is very important points in D block elements in one shot. Okay. First point is, what are transition elements? See, actually the elements belonging to the D block of the periodic table are called as transition elements. See here the elements which are shown in yellow color, these are D block elements, and these D block elements are otherwise called as transition elements. Okay. See now, why D block elements are called as transition elements? Actually, if this is the periodic table. In the periodic table, these elements are placed between the highly positive S block elements and highly electronegative P block elements, and they show a transitional behavior between the two, that is between the highly electropositive S block elements and also the electropositive P block elements. This is the reason why the elements of P block elements are referred as transition elements. Understood? If so, why the transition elements are also called as D block elements? Actually, in these elements, the differentiating electrons enter into n-1 D subshells. Okay. See the electronic configuration from scandium to zinc. See here the electrons are added up in the subshells, D subshells. Understood? N-1 D subshells, right? See, all the electrons, successive electrons are filled in the D subshells. That's why they are called as a D block elements. Understood? Actually, to which group of the periodic table do the transition elements belong to? Actually, this transition element, D block element, is situated in the middle of the periodic table. Okay, it is situated in the middle of the periodic table. That two from between the group 2. Okay, this is group 2 and this is group 13. So in between lies the D block elements, that is from 3 to 12. Understood? See, the transition elements are classified into 4 horizontal series called as transition series. Okay. So this is the first transition series. Okay, let me explain with this, right? So this is the first transition series or the 3D series. This is the second transition series or the 4D series. This is the third one, and this is the fourth transition series or the 6D series. Okay, the first transition series or the 3D series, this series corresponds to the filling of 3D subshells and consisting of 10 elements from scandium to zinc. Okay, that is from scandium 21 to zinc 30. Okay, that is from scandium to zinc. Understood? And these elements belong to the fourth period, right? First period, second period, third period, and the fourth period of the periodic table. Understood? So the second transition series or the 4D series, this series, it corresponds to the filling up of 4D subshells and consists of 10 elements from yttrium. Okay, from yttrium to cadmium. Understood? And these elements belong to the fifth period of the periodic table. Fifth period of the periodic table. And next comes the sixth period, and next comes the seventh period. Actually, these transition elements, they have the electronic configuration, general electronic configuration of the type n-1, D 1 to 10, ns 1 to 2. Okay. The 3D, 4D, 5D, and 6D series of the transition elements corresponds to the filling up of 3D, 4D, 5D, and 6D subshells respectively. Understood? So now there's a question for you. Would you regard zinc, cadmium, and mercury as transition elements, where these elements are actually they are in the end of all the series, right? Is it not? The end of all the series we have the zinc, cadmium, mercury, and the question is, would you regard the zinc, cadmium, and mercury as transition elements? Actually, the zinc, cadmium, and mercury are not regarded as transition elements due to the absence of partly filled d orbitals in them and in their commonly occurring ions also. Actually, this transition, because the transition elements may be defined as those elements which possess partly filled, that is half filled. Okay, it's not completely filled. Okay, partly filled d orbitals in their elementary form or in their ions existing in chemically significant oxidation state. Understood? So this zinc, cadmium, and mercury cannot be regarded as transition elements. Understood? Next important one is, how do atomic radii and ionic radii of transition elements vary across a particular series? Okay. See, I have given a tabular column which consists of the different elements of the first transition series, second transition series, and the third transition series, and also their atomic radii. Understood? See here, it's varying differently in a different series. Actually, in general, the atomic radii of transition elements belonging to particular series decreases with increase in atomic number. See, as we move from scandium to zinc, the atomic number increases, is it not? But the atomic radii, gradually it is decreasing. However, there is a slight increase in the atomic radii near the end of the series. See, at the end of the series, in all the series, that is in first series, second series, and also in the third series, at the end we could see a increase, okay, an increase, slight increase in the atomic radii. See, let me explain why there is a increase, slight increase at the end of all the series. Because towards the end of the series, towards the end of the series, the electron repulsion between the added electrons in the similar orbitals predominate over the attractive forces due to increase in nuclear charge. Can you understand? Since the electrons are added up in the similar orbitals, there will be a repulsion. Okay, there will be a repulsion. So because there is a repulsion, see already we know that, see, since we are having the nuclear charge here, and the electrons will be getting added up in the outermost orbitals, if not the electrons. So the added up electrons, the electrons are getting added up in the same orbitals, and because of this there will be repulsion between the electrons. So this repulsion will be predominating over the attractive force. Already there will be an attractive force between these electrons and the nuclear charge, and the repulsion will be greater than, it will be predominating the nuclear attraction between the attractive forces due to increase in nuclear charge. This results in the expansion of the electron cloud. Understood? This can be clearly understood by taking the example of the elements of the first transition series. See, up to chromium. Okay, up to chromium, the electron present in the 3D subshells are unpaired. Understood? Okay, because the electrons will be like this: 3D5, 4s1. Okay, so up to chromium, understood? Up to chromium, the electrons present in the 3D subshells are unpaired, and the electron-electron repulsions are not significant. So when you move down the series, the electron starts to pair up in the 3D subshells, and therefore the electron-electron repulsion becomes progressively more and more significant with increase in the number of paired electrons. Okay, so from manganese to nickel, see, from manganese to nickel, the electron-electron repulsions are almost counterbalanced by the attractive forces due to increased nuclear charge. Okay, so this is why the atomic radii remains almost constant from manganese to nickel. When we reach towards the end of the series, the number of paired electrons are maximum. Can you understand? And therefore, the electron-electron repulsion becomes greater than the attractive forces due to increased nuclear charge. This causes the electron cloud to expand. That's the reason why there is an increase at the end of the series. Understood, students? Next important one is the metallic properties and lattice structures. See, what type of lattices are possessed by the transition elements? Actually, all the transition elements are metals. They have simple HCP, that is hexagonal close packing, cubic close packing, or body-centered cubic close pack structure. Lattices which are characterized by a true metal. Okay. See, almost all the transition metal elements exhibit typical metallic properties like metallic luster, malleability, ductility, high tensile strength, high thermal and electrical conductivity, etc. I have given the tabular column of the different elements present in the different transition series and their lattice structures. Okay, scandium, titanium, vanadium, chromium. See here HCP, BCC, CCP. Okay, so almost except zinc, cadmium, mercury, and manganese, they have one or more typical metallic structures at normal temperatures. Okay, why that's that exception? So actually, the metallic character of these transition elements may be attributed to the lower ionization energies and the presence of several vacant orbitals in their outermost shell. See, these transition metals will be having vacant orbitals in their outermost shell. This vacant orbitals, this favors the formation of metallic bonds in them. Okay, this is why the transition elements exhibit metallic character. Actually, the hardness of these metals are said to be more hard. Okay, transition metals are said to be more hard. The hardness of these metals indicates the presence of covalent bond in them. Okay, what type of bond is there in the transition metals? Specifically covalent bonds. Okay, this may be possible. This covalent bond is possible only due to the presence of unpaired d electrons in them. Okay, so the d orbitals containing unpaired electrons may overlap to form the covalent bonds. Okay, higher the number of unpaired electrons present in the transition metal atom, more is the number of covalent bond formed by it. Can you understand? If more number of unpaired electrons are there, then the covalent bond will be more. Okay, it will be strong. Greater will be the strength and hardness of the metal. Okay, see here chromium, molybdenum, and then tungsten. they have the maximum number of unpaired electrons. They have the maximum number of unpaired electrons, okay, the electrons. Therefore, these metals are said to be very hot. They are said to be very hot. Can you understand? Whereas zinc, then cadmium, mercury are not very hot because they do not have unpaired d electrons. Can you understand? They do not have unpaired d electrons. They are completely filled with d orbitals and no unpaired electrons are there. So that's the reason why they are not so hot. Can you understand? Next is the formation of the colored ions by these transition elements. What type of transitions impart color to the transition metal ions? Actually, most of the compounds of transition metals are colored both in solid state as well as in the aqueous solutions. Okay. See, actually, the color of the transition metal ion is due to the DD transition. So that's very important. Because of the DD transition taking place between the splitted d orbitals. Okay. See, all the transition metals possess one or more electrons in n minus 1 d subshell. Is it not? All the transition metals will be having the having electrons in n minus 1 d subshells, right? And what happens here? We all know that the d orbital, d subshell, it has a 5 orbitals. It's not, see, d subshell has 5 orbitals, namely dxy, dyz, dxz, dx square minus y square, dz square. Is it not? And in an isolated atom or an ion in a transition element, all the 5d orbitals are at the same energy level. Okay, before pairing up. Okay, before undergoing any reaction, all the 5d orbitals will be in the same energy as said to be, that is, and are said to be degenerate. However, under the influence of any ligand, if any of the ligand is approaching the d orbital, what happens? The d orbital gets destroyed and they split up into two groups of orbitals called as T2G group and EG group. Can you understand? It is called as crystal field splitting. Okay, and these two sets of orbitals will be having different energy levels. Actually, a visible light can induce an electronic transition between these two set of splitted d orbitals. Okay, such transitions taking place between the two groups of the splitted d orbitals are referred to as dd transition. Actually, the transition metals, the transition metal atoms or the ions possess one or more unpaired electrons. When visible light falls on this transition metal or compound or hydride ion, the unpaired electron present in the lower energy d orbitals will be getting promoted to the higher energy level d orbital. Okay, this is called as dd transition. Since the energy involved in the particular dd transition is quantized, only a definite wavelength gets absorbed. Only a definite wavelength gets absorbed in the process. The remaining wavelength present in the visible light get transmitted. It will be getting transmitted back. Understood? Therefore, the transmitted light shows a complementary color corresponding to the absorbed wavelength. Okay, and the compound or the hydride ion shows a same color. Can you understand? For example, Ce2 plus ions are absorb red radiation and transmit the complementary green-blue radiation. This is why the cupric salts appear greenish blue in color. Similarly, hydrated CO2 compounds absorb blue-green radiation. Okay, and then while coming back, while transmitting, it transmits the complementary red color. Okay, this is why the hydrated CO2 compound appears a red in color. Can you understand? Now that's a question. What is the color of the transition metal ions having completely filled and empty d orbitals would be? Okay. So they are asking the question, what would be the color of the transition metal ions if their orbitals are completely filled or either empty? Okay. Actually, the transition metal ions having completely filled d orbitals or completely empty d orbitals are colorless. Can you understand? They are colorless. They don't have any color. This is because in the former case, that is when it is in the completely filled state, there are no vacant d orbitals for the promotion of electrons. Okay. While in the later case, there is no electron available for dd transition. So since there's no dd transition taking place in these two cases, the transition metals will not be having any color and they are said to be colorless. Can you understand? Next important property is the oxidation state. See, most of the transition elements exhibit several oxidation states and variable valencies in their compounds. Understood? So the ability of the transition elements to exhibit several oxidation states is the characteristic property of that particular element. Okay. So I have given all the elements of the first transition series. See here, what is the what are the different types of oxidation states? See here, this scandium is having plus 2 plus 3, titanium plus 2 plus 3 plus 4, vanadium plus 2 plus 3 plus 4 plus 5. And here also this chromium manganese, they are having the maximum plus 2 plus 3 plus 4 plus 5 plus 6. Is it not? So different several oxidation states are possible for the various elements present in different transition series. Okay. And now there are some questions under this oxidation state, very important questions. What is the common oxidation state of the elements of first transition series? Actually, the most common oxidation state of the elements present in the first transition series is plus 2. See, everything has plus 2. Is it not? All have plus 2, right? This indicates that after scandium, the d orbitals become more stable than the s orbital. Understood? Next question is, what type of bonds are formed by the transition elements in plus 2 and plus 3 oxidation states? Actually, the bond formed by the transition metals in plus 2 and plus 3 oxidation states are mostly ionic. They are mostly ionic. Understood? So, the bond formed by those compounds which have the plus 2 and plus 3 oxidation states are ionic. Okay? What is the highest oxidation state shown by a transition element? But actually, the highest oxidation state is plus 8, and we could see that in ruthenium. Okay, we can see it in ruthenium, right? Ruthenium in second series, in second transition series. Okay, in second transition series, and it is plus 8. And also in third transition series, we have for osmium. Okay, for osmium we have, right? So these are the highest oxidation states shown by the transition elements. Understood? Next one, in what type of compounds do the transition elements exhibit their highest oxidation states? In covalent compounds. Okay, the covalent compounds here in ionic. Okay, in plus 2 plus 3 it is ionic. Where on the other hand, the bonds formed in the higher oxidation states are especially covalent. Next, do transition elements form compounds in the oxidation states 0? Actually, the transition metals also form compounds in low oxidation states such as plus 1 and 0. Okay, it is possible to form compounds in plus 1 and plus 1 in plus 1 and 0. Okay. For example, the oxidation state of nickel in nickel tetracarbonate, that is NiCO 4 times, okay, is 0. Actually, the oxidation state of nickel in NiCO4 is 0. But it is also forming a compound. Is it not? Right. Write all the possible oxidation states of chromium and manganese. See, I have discussed the important questions coming under oxidation states of D block. Okay. So write all the possible oxidation states of chromium. See here, it's very important to learn certain elements. Okay. See here, plus 2, plus 3, plus 4, plus 5, plus 6. Okay. Plus 2, plus 3, plus 4, plus 6, plus 7. So these are the different possible oxidation states of chromium and manganese. Can you understand? Next important property is the magnetic behavior. Most of the transition elements and many of their compounds show paramagnetic behavior. What do you mean by paramagnetic or diamagnetic? See, paramagnetic substances are those substances which are attracted by the magnetic field. Okay, and the phenomenon is called as paramagnetism. Okay, so a substance show paramagnetic behavior only when it contains one or more unpaired electrons. That's very important. Okay. So ferromagnetism is a special case of paramagnetism in which a substance acquires permanent magnetic momentum. Okay, whereas in diamagnetic substance, the substance will be repelled by the magnetic field and they have paired electrons. Okay, and that phenomenon is called as diamagnetism, right? So why do most of the transition elements show paramagnetism? The reason is most of the transition elements and many of their compounds show paramagnetism. Actually, this is due to the presence of unpaired electrons in n-1 d orbitals. Okay, in n-1 d orbitals, we have unpaired electrons. As the unpaired electrons increases from 1 to 5 on moving from left to right, okay, from left to right in the first transition series, from left to right in transition series, the paramagnetic character of transition metal ions increases. Can you understand? When you move from left to right, the number of unpaired electrons increases, and that's why the paramagnetic character is also increasing. Okay, the maximum paramagnetism is found in the middle of the series. Can you understand? Maximum paramagnetism is found in the middle of the series. On moving further, the magnetic behavior decreases with increase in the number of unpaired electrons. Can you understand? The transition metal ions or metals or ions having paired electrons show diamagnetic behavior. So at the end it changes. In the beginning the paramagnetism is very high, and in the middle it becomes a little there's an increase again, and at the end obviously there will be an increase in the diamagnetic character. Okay, so the paramagnetic behavior of a substance is expressed in terms of magnetic moment, which is expressed in Bohr magneton. Okay, see, the next important one is complex formation. The transition metal ions form a large number of complex compounds. Greater the tendency of the transition metal ions to form the complexes due to the small size of the transition metals, the high nuclear charge, and availability of vacant d orbitals. Okay, see this vacant d orbitals of suitable energy. That's the availability of this vacant d orbitals of suitable energy to accommodate lone pair of electrons donated by the ligands. It's the main reason for the formation of the complex. Okay. So the next important one is the formation of the interstitial compounds. See, the transition metals form large number of interstitial compounds with elements such as hydrogen, carbon, nitrogen, boron, etc. Okay. See, these interstitial compounds are those compounds which are formed when small atoms like hydrogen, carbon, nitrogen get trapped inside the crystal lattices of the metals. Okay, these small atoms of these elements, the small atoms of these elements like hydrogen, carbon, nitrogen, boron, etc., they occupy the vacant spaces in the lattice of transition metals, resulting in the formation of the interstitial compounds. Okay, the formation of an interstitial compound does not alter the chemical behavior of the parent transition metal. Okay, it will not affect the chemical character or the property. However, many physical properties such as density, hardness, rigidity, malleability, ductility, electrical conductivity, etc. gets modified considerably due to the formation of these interstitial compounds. Can you understand? The important physical and the chemical properties of the interstitial compounds or the melting point of these compounds are quite high, higher than those of the pure metals. Okay. So the pure metal, when you take into account the interstitial compounds formed by these transition metals, they have the melting point little high and higher than those of the pure transition metals. Okay, and then the interstitial compounds are very hard. The hardness of this some of the compounds are comparable to this that of the diamond. Okay, they exhibit conductivity similar to that of the pure metal, and they are chemically inert. So these are the different characteristic features of these interstitial compounds. Can you understand? Next important one is the alloy formation. Actually, the transition metal ions form large number of alloys among themselves. These alloys are very hard and often have high melting points. Okay. The reason why they are forming the alloys is the tendency of the transition metals to form the alloys among themselves may be attributed to the fact that their atomic sizes are very small and also very similar. Okay, they are very small and they are very similar, right? Due to almost similar atomic sizes, one metal can easily replace the other metal, okay, from its lattice to form a solid solution called alloy. This is why the transition metals are miscible with one another in the molten state. Okay, so the molten solution of two or more transition metals on cooling gives a corresponding alloy. Can you understand? So what is the reason for the formation of the alloy? Because the transition metal ions have almost similar size. So it's very easy to substitute one metal by the other metal. Okay. So the formation of alloy is very easy here in the case of transition metals. Understood? The next one is the formation and nature of oxides. The first row transition metals react with oxygen at high temperature to form various types of oxides. See here I have given examples. So I have given the first row transition elements, and these are the different types of oxides formed by these elements. Okay. So and under this category we have three types of oxides: acidic, basic, and amphoteric. Okay. See what is the nature of the oxides or the first row transition elements formed in the lower oxidation states. In general, the oxides formed in the lower oxidation state of the metals are basic, while those formed in the higher oxidation states are acidic. Okay, and those are between the higher oxidation and the lower oxidations, that is intermediate, they are amphoteric in nature, and this is perfectly explained in the case of manganese. Okay, see here in the case of manganese, when the oxidation state is very low, it is basic. Okay, when it is very high, it is acidic. In between basic and acidic, we have the amphoteric. Can you understand? Write the general formula of oxides of first row transition elements. See here, general formula we have MO, Okay, M2O3, M3O4. Okay, these are the general formats. MO2, then M2O5, and then MO3. So these are the general formats or formula of the oxides of the first row transition elements. Understood, students? Next important one is melting and boiling points. Melting and boiling points of transition metals are very high as compared to those of the representative elements. Okay. The melting point of the melting point first increases, attains a maximum value, and then steadily decreases as the atomic number increases. Okay. So the reason for this one is the high melting and the boiling point of the transition metals are due to their close packed structures. That's the main reason. Okay. In these structures, the transition metal atoms are held together by strong metallic bonds, which have considerable covalent character. Okay. Therefore, it requires considerable amount of energy to break the metallic bonds in order to melt the metal. Okay. Consequently, those metals will be having very high melting and the boiling points. Understood, students? So the high melting and boiling point of the transition metals are due to the closed packed structures. Can you understand? Actually, the strength of the metallic bond depends upon the number of unpaired electrons. Okay, so greater the number of unpaired electrons, stronger will be the metallic bond. So automatically, it requires lot of energy to break the bond. Okay, whereas in the case of zinc, then cadmium, then mercury, they have no unpaired electrons. They have no unpaired electrons. This is why these metals are soft and they have low melting and boiling points. Okay, so mercury is a liquid at room temperature and has melting point 234 Kelvin. So the unexpected lower melting point of manganese and technetium. So where is it? This is manganese. Is it not? Here we have the manganese and technetium. Here we have the lowest melting point. And probably this is due to the complicated lattice structure of these two metals. Okay. See, technetium and manganese, they have very low melting point, and this is due to the complicated lattice structure. Understood? That's the reason why they are having very a low melting point. Understood? So the next one is enthalpies of atomization. What is by atomization actually? The enthalpy of atomization. Change in enthalpy when one mole of bond is completely broken into atoms in the gaseous phase. That is called as enthalpy of atomization. Okay. So the transition elements exhibit higher enthalpies of atomization, and the elements of second and third transition series have greater enthalpies of atomization compared to the first transition series. Right? What's the reason? The higher values of enthalpy of atomization of the transition elements may be attributed to the presence of large number of unpaired electrons. So in most of the cases, we are explaining in the case of unpaired electrons. So because of the presence of large number of unpaired electrons in their atoms, they have higher values of enthalpies. Due to the presence of large number of unpaired electrons in their atoms, they pose a strong intraatomic interaction, due to which they have strong bonding between atoms and hence higher values of enthalpies of atomization. Can you understand? Since they are having large number of unpaired electrons, can you understand? Since the number of unpaired electrons are going on increasing, their interaction increases, okay, intraatomic attraction increases, and it becomes very strong, and the bonds becomes very strong, and hence it requires higher values of enthalpies of atomization. Can you understand? Next important one is the ionization enthalpy or ionization energy. Actually, the ionization energy of transition elements lies between S block and P block elements. That is, they are having higher values. They are higher than that of S block elements and lower than that of the P block elements. Okay, I have given the first ionization energy, second ionization energy, and third ionization energy of the first transition series. Okay. So first let me explain the reason why the ionization enthalpy of transition metals are quite high and why it lies between the S block and the P block elements. Okay. So actually the atomic radii and the nuclear charge of the transition metals lie between those of S block and P block that we know, is it not? They possess smaller atomic radii and higher nuclear charge as compared to that of the S block elements. But reverse is the trend when compared to that of P block elements. When you take into account the P block elements, it's entirely reversed. This is why the ionization enthalpy of the transition elements lie between those of S block and P block elements. Can you understand? The first ionization enthalpy increases with atomic number across a given transition series, although the increase is not very regular. What's the reason? Actually, the increase in ionization enthalpy with the increase in atomic number across a given series is due to an increase in the nuclear charge with the increase in the atomic number. Understood? What can you understand? The increase in ionization enthalpy with increase in atomic number again across a given series is due to increase in nuclear charge with increase in atomic number. As our nuclear charge increases, automatically attraction increases. So we have to spend much energy to remove the outer electrons present in the outermost orbit. Okay. So the added electrons enter into n minus 1 d subshells. Okay, the electrons will be getting added up to the n minus 1 d subshell. Okay, and shield the valence electrons from the nucleus. So the added up electrons will be shielding the outermost electrons from the nucleus. Okay, thus the effect of the increased nuclear charge is opposed by the screening effect of n minus 1 d electrons. This is the reason why the increase in ionization enthalpy with increase in atomic number is rather slow and not very regular. Can you understand? Well, fine students, I hope you might have understood what I have taught today. Let me meet you with another important topic in my next session. Until then, it's Dr. Anita, GR Chemistry Mentor, signing off from you. Thanks for watching.